Okay. Well, yeah.
Maybe you, yes, maybe you repeat the question to.
Right. I think that it was written while my seminar was going on. That's why I
Yes, it was written there.
Right. Yeah. So the question is, even before having complete interaction theory for high spins, we may have observable consequences. For example, if a theory is defined only in the ADS space, it predicts that space. Any other prediction? So I didn't want to confine the comment in the chat because it's probably can be extended. Well, first of all, of course, number one, actually, the fully nonlinear theory isn't defined only in ADS. There are more complicated. Well, first of all, DS is also a reasonable vacuum from the point of view of the Vassiliev equation. There could be more complicated vacua, in fact. So it's not like ADS is the only thing and that's the only prediction. Also, there could be this is definitely predictions in principle go much beyond that. For example, if the correspondence, if one trusts the proposed holographic correspondence with free CFT, essentially one can extract correlation functions for the boundary theory starting from the bulk theory. There's been proposal about that. So, in fact, the free part actually is already tested and works. It needs to be understood though. And the answer to this is also partially complicated by the fact, I would say, that it is debatable also what to expect in some sense, because in principle, even the boundary theory could be more complicated than the holographic boundary theory to Misha's high spin gravity could be more complicated than what's been proposed, what we expect. So to make it short, I mean, of course, there are other predictions, but there's a lot of work to be done to exactly assess what these are and compute them. Yeah. I don't know if that answers, by the way, his question, but I hope so.
Well, I don't know if the author of the question is in the audience. I have not checked yet, but since he does not respond, let's.
Maybe not.
Yeah. So, other questions to Carlo, please.
That questions was mine.
Hi.
The questions about predictions of the high spin theories. Also concerning to the resonances was mine. I hoped that there are indication, but their name is in Russian. Maybe this is somehow difficult to identify the author of the questions. Okay, thank you anyway.
No problem. I hope that partially answered your question.
Yes, yes.
Okay, at least. Okay.
Other questions to Carlo, please? Well, maybe I'll ask the question. So the Fronsdal fields, maybe I have not understood well, how do they arise explicitly? So in a way, you should go from the frame-like to metric-like formulation. So in a sense, they should be a composite object of frame-like fields somehow, right?
Absolutely, yes.
Can you comment on this, maybe?
Yes, so this definitely, I didn't have time to comment. I didn't even include it in the slides because it would take us far away from the main point. But the issue is that Vassiliev equation, in fact, it's much, the formulation is that the unfolded one, of course, it was invented for that purpose, that Ehang has just presented in his talk as well. So the idea is that those generating function that I showed you, both for the gauge fields and the zero form, they are having an expansion in these oscillators, in particular the fiber oscillators Y. They have an infinite expansion in power of that. And the coefficient of this expansion in Y provide exactly the set of fields that are necessary for the unfolded formulation of Fronsdal equation. Fronsdal equation are equations formulated in terms of the second order equations, formulated in terms of metric-like fields with more indices, essentially. And the unfolded formulation, what it does is that, first of all, it reformulates the story in terms of frame-like fields. So an extension of the field-bind formulation of gravity, there is a field-bind-like, and there is, say, auxiliary connections in the gauge field sector, plus an infinite set of zero forms for every spin S field. So in the zero form sector, the spin S field is, spin S sector is infinite dimensional even. And that is because it is, that contains actually all the non-trivial, on-shell non-trivial combination of derivatives of the physical field. So it's got to be actually infinite dimensional to make sense. Of course, all of these tensors are essentially derivatives of the physical field, and the physical field is embedded into a specific projection of the if you want, of the field-bind-like field, just as in gravity in that sense. And the whole set, the whole kit, essentially gives us Fronsdal equations. Via linearization of Vassiliev equation gives us automatically Fronsdal's equation in the unfolded language. So they are a little bit more complicated, but for example, just to give you a flavor of this, the simple Klein-Gordon equation in the, as a lot of you already know very well, the Klein-Gordon equation is written in terms of an infinite chain of equations that are tensor identities. So the derivative of the lowest of the actual scalar object of the chain is set equal to a rank 1 tensor. Derivative of the rank 1 tensor is set equal to the rank 2 tensor, etc., stuff like that, a bit like a Hamilton-like system with specific constraints on these higher rank tensors, trace, essentially they're bound to be traceless. Therefore, it's a specific solving in chain, putting essentially the second constraint into the first and taking a trace condition that encodes the Klein-Gordon equation. So somehow it's a little daunting at first, maybe, and first time you see it, you don't understand what's the advantage of this. But then, of course, there's a reason why one does that. It pays off when it comes to generalizing to higher spins, to a whole multiplet of higher spins, and it gives a more systematic way of controlling all the higher derivative couplings that arise naturally. So I hope this answers your question. So, and in other words, maybe I should actually share. If I go back and share the slides here, I can just show you. I'm screen sharing, but not what I'm, sorry.
Yes, you share.
Stop share, and then I will try again. Yes, it's here. And again, okay, let me then.
No, but maybe you can.
I think now you should be able to see full screen. Okay, so it's completely unrecognizable if you've never seen it, but once you go to the linearized Vassiliev theory, you find in the proper frame, in the proper choice of field variables, these two equations on these two generating functions, W1 and C1. And I totally agree that from here you wouldn't think it, but these contain exactly Fronsdal equation. In the spin S sector of this one that I'm highlighting, in every spin S sector, this decomposes into this unfolded chain that reduces to Klein-Gordon for the scalar, unfolded chain that reduces to spin S Bachmann-Bickel equation for all the Weil tensors, so Maxwell and then Weil, and then its generalization for spin S. And this other equation is a set of equations that sets a certain combination of derivative of the gauge fields contained here equal to the curvatures contained in C1. The meaning is the same as this equation that Ihan was showing in his seminar. So the ones that have the components here of the curvatures that are identical, some of them are set equal to these curvatures, and these are free to fluctuate. Others are set to 0, and these are torsion-like constraints. So the combination of all this equation helps resolving back essentially certain components as auxiliary, certain others as physical, and imposes the Fronsdal equation on the physical one. So in this context, this is the definition of Fronsdal fields, if you want, extracted from the Vasiliev system.
Okay, thank you. Yes. Other questions to Carlo, please? Okay, if not, then let's give the word to Karapet. There were hands raised during his talk by Zhenya Ivanov and Dima Ponomarev. So maybe Zhenya can start and ask the question. Zhenya, are you there?
Maybe not.
Maybe not. Okay, then Dima, would you like to ask? Yeah, please.
Yeah, what about Karapet? Is he here?
Yes, Karapet is here. Yes.
Okay. Yes, so because of this kind of lags and freezes, I was not sure that I understood. So at the end, there was a discussion about representations of a colored Poincare. Was it in 3D or it was in other D? In 3D only, right? And you said eventually it looked like point particles, but I would say if you do something like Wigner-induced representation method, it's more about invariant wave equations, right? So what was it?
Yes.
Particles?
You can do both. So you can do both. So what we did, let me share the screen. We construct particle actions, but it's true that one can also mention it here, but one can also use the same method to develop wave equation. Then the corresponding field would be living in the full colored Minkowski space. And depending on which action we take, so here there are two possibilities. One is the geometric action that I mentioned. It has not the full matrix equation, p squared plus m squared, but it's tracing. So correspondingly, the solution space is much bigger, while the one that we derive by induced representation is kind of like an irreducible one that contains just n+1 many orbits, and this one would have equation that is a matrix acting on the wave function. And by the way, I didn't talk about that, but we assume that we are dealing with the scalar particles in the sense that they are the trivial representation of the little group. So the little group here is U1, S1, S1. So if we are in n equal 1 case, we have just the, and that's the rotations in 3 dimensions. But if we have full colored Poincare algebra, then for this momentum, the little group would be U1 plus S1 plus S1. And of course, there is a lot of possibilities of different representations for each factor here. And correspondingly, there may be a zoo of many possible particles. But we are talking only about the trivial representation. And for this, we construct the scalar particle action, and so the function would be a scalar, but depending on the colored Minkowski coordinates, and then the equation, depending on which of these cases we take, the equation on it would either. But for the scalar equation, it is also straightforward to write a field theory action. But for the matrix one, it's not so straightforward. This somehow seems similar to the equations of motion have transformed under the different representation of colored Lorentz here, but even just Lorentz, compared to the fields themselves. So just contracting them with the fields and writing an action wouldn't work so simply. So we don't know how simply to write an action for this model, this irreducible one, let's say. While for the geometric one, it seems that some sort of generalization of Klein-Gordon equation would work. But yeah, we didn't explore much this field theory direction. I don't know if this answers.
Yeah, thank you. By the way, is it unitary, the scalar representation of the colored algebra?
So yes, we can define unitarity. So of course, from the little group, we have the what was that? Yeah, and then we just act with the boosts to generate the most general one, and there is a way to define unitarity for the algebra that this representation would satisfy. But there is something weird in the sense of physical understanding, because as I mentioned quickly, here the corresponding equations that I was mostly concentrating, that are the matrix equations. Here the solution space, two of them can be understood as some sort of positive energy, negative energy, L equals 0 and L equal n. But for the middle ones, what we realized is that it doesn't seem they don't seem to have a bounded energy from either side. So in this sense, I don't know if I mean, unitarity is a different issue. We can define a norm, and it seems that we can define, even for this model, unitary representation. But somewhat related issue is also the boundedness of energy, which in this case is not satisfied for all the orbits. So this aspect we didn't completely study further yet.
Thank you.
Okay, there was a raised handed by Igor Bandas, but then it disappeared. Igor, would you like to ask a question?
I have also a question.
Yes, Zhenya, we were waiting for your question, but then...
I have some general question to Krapets. How do you avoid standard Coleman-Mandula theory?
Yeah, that's a good question. So from the color
purification of Poincaré and Donaldson.
Yes. So there are two things I talked about, but we don't yet have their combination in a sense. So one is the colored gravity. We can write an action in 3 dimensions. It does not have bulk propagating degrees of freedom, so Coleman-Mandula doesn't apply there. While when we try to take this algebra and study the representations, we go to a different setup where actually we extend the space-time. So we have colored Minkowski, where the particles that are moving, they move in higher dimensions actually. So it's an interesting question to understand. So these extra coordinates, one can either compactify or in some way expand in terms of these coordinates and study what the 3-dimensional spectrum is, and it would be infinite spectrum involving there might exist infinite number of massless fields also in this spectrum, and it is not completely the setup of Coleman-Mandula, but it might also be that we need to break these extra symmetries to have non-trivial scattering in 3 dimensions, in the sense that one way or another one has to get rid of these extra dimensions.
Okay, excuse me.
Yes, please, Zhenya.
Okay, I have some related question because you mentioned coupling of particle to Yang-Mills field, but I should say that it is known for a long time how to couple particle to non-abelian Yang-Mills field. You just should introduce some nonlinear realization of gauge group and add some additional coordinates to X coordinates, parameterizing cassette of this gauge group, a kind of harmonics on the gauge group. And then you can write the action which generalize coupling to abelian.
Yes, I agree. What you are referring to, I think, is known as Wang equations, right? So this is a possibility, but in the same way, one can use for electrodynamics, one can use coupling without introducing this Maxwell algebra. But it seems to be more natural from 2 different perspectives to introduce this algebra. First, you try to extend the symmetries instead of reducing them, although eventually you will need to break these symmetries. And on the other hand, this Maxwell can be generalized to higher Maxwell, which is what Thomas and Kleinschmidt studied recently, which is that one can basically expand in the different modes of the Maxwell field. So the constant one will generate this Maxwell algebra, but if you want to have non-constant background, you even extend the symmetries. So in this sense, it is somewhat similar to the unfolding setup of Sylvia theory, introducing more fields corresponding to configurations there are, and basically taking very large algebras and then breaking in some smart way the symmetries to describe the interacting particle. So this method, if you want to generalize it to use for Yang-Mills, would require to so already at the constant background of Maxwell, that if we generalize to Yang-Mills, we would need to color decorate this Maxwell algebra, which also contains Poincare. So that's the idea that we thought then it would be useful to have first colored Poincare, then extended to colored Maxwell, which would be much larger than what one needs in principle, but might be interesting example how to do it alternatively.
Okay, but my remark was that exists some minimal way of coupling of particle to non-abelian gauge fields without modifying Poincare group, etc. It was just my remark.
Yes.
Okay.
Okay, then probably the last question by Maxime. Maxime, please.
Okay, thank you. I just wanted to ask Karapet to maybe clarify a bit, because it was a very bad sound and interruptions of the connection. What is, I remember, Karapet, you introduced colored Minkowski space. So could you please repeat definition and maybe comment if it has something to do with non-commutative space? Perhaps I am totally wrong, but it sounds a bit similar. Just to clarify.
So yeah, Minkowski. So if you have a colored Poincare algebra, so basically the generators of translations, color decorated now. So it's natural to introduce extra coordinates for these translations. And this is what we do. So here we have basically the regular translations and corresponding coordinates. Then there are color translations and coordinates for them with this SUN adjoint volute. And then there are also this another Lorentz singlet translations that are again in SUN but commuting. And so for each of them we introduce new coordinates. So then on top of the regular Minkowski coordinates, we have much more. This is what.
But what is the algebra? What does it mean? This space is it's just a commutative space, perhaps with the action of
Yes.
what this colored Minkowski acts on it. Is it a coset? Just
Yeah,
what is the meaning of this?
The action of colored Minkowski is clear that the colored Lorentz part rotates it, while colored translation just to move. So in a sense, it's to regulate.
So you make the color this internal transformation geometrical in this space, right? So they like act on coordinates. Yes, I see.
Yes.
Okay. So thank you.
May I comment something?
Yes, please. Joachim, that's you. Okay, please.
Yes, okay. I would like to comment that if one considers a configuration where xai equal to 0, this space is this configuration's map in itself. Therefore, that will be the natural space to make contact with the Bond equations. Only that.
Thank you.
One can identify this extra y coordinates with the coordinates that one needs to introduce for Wang equations. As
yes.
Also, Evgeny mentioned.
Thank you.
Okay, thank you. I think we have arrived at the end of our discussion session. Let me thank, on behalf of all participants, all the speakers, and remind that the next session starts in 30 minutes, in half an hour. So, see you there.
Dimas, thank you very much.